Hello, everybody. Welcome to this session today at FairCon. My name is Luke Bader. I'm Director of Membership and Programs today at the Fair Institute. And today I am, during this session, happy to introduce Doug Hubbard to present on his session titled The Team as a Measurement Instrument. And he's going to elaborate and expand on that a little bit. A little bit about Doug before we get started here. He is the president of Hubbard Decision Research and the inventor of the powerful Applied Information Economics, or AIE method. Over the last 20 years, he has completed over 100 projects of the application of the AIE to solve current business issues in many areas, including IT benefits and risks, including in cybersecurity. His methodology has received critical praise from the Gartner Group and Forrester Research. And he's the author of multiple books as well, most famously How to Measure Anything, Finding the Value of Intangibles in Business, one of the all-time and best-selling books in mathematics. Mr. Hubbard is published in the prestigious science journal Nature, as well as publications in the American Statistician, CIO Magazine, Information Week, DBMS Magazine, Architecture Boston, and Analytics Magazine. So with that, Doug, I will turn it over to you for the presentation. One reminder for everybody, you can please put any questions that you have in the chat, and we will be answering those as the presentation goes along. So Doug?
Thanks, Luke. For today's presentation, I wanted to focus on what I thought could be a pretty powerful set of methods we've been researching recently. It has to do with our calibration research. It's under the banner of the team as a measurement instrument. I think this should be some pretty potentially powerful methods, since most organizations, when they try to elicit estimates of the likelihoods of various events, as in cybersecurity, from subject matter experts, they're usually doing it with a group of people. And that changes things when you use a group to estimate things. There's a lot of research behind that. I'm going to be talking about some of that research and some original research on our own. But for some context, for those of you who might not be familiar with my work, I'll just review a couple of quick things, and I'll refer you to my previous presentations and books for further information on each of the points I'll talk about. All of my books and all of my presentations have a common theme. The common theme is that we're making decisions under uncertainty and we're trying to improve them using whatever methods we can. We're looking at scientifically valid, empirically demonstrated methods for measurably improving estimates and decisions made under a state of uncertainty. These are just my books I've written so far. They deal with that kind of problem in a variety of industries and professions, including cybersecurity risk. If you know my work, you know I spend some time trying to debunk some very popular methods that are qualitative and subjective. Not that all subjective methods are wrong. We use lots of subjective methods. I'm going to be talking about subjective methods in detail today, about how they can be improved within a group by mathematically aggregating them. But some methods make things worse. And the risk matrix is my favorite villain along these lines. There's a lot of research that shows that they don't actually help. In fact, they may actually add error to your estimates and decisions. These are just a couple of the bigger studies that have been done over the years, some of the more influential studies. Here's a couple of choice lines from those studies. Risk matrices should not be used for decisions of any consequence, or risk matrices can be worse than useless. That's pretty harsh. And if you want to see more research behind that argument, not just these two papers, but also the research in unrelated areas like the psychology of using qualitative scales when we evaluate things, that actually introduces other sources of error itself. I also spent a lot of time describing methods that are shown to measurably improve estimates and decisions. For example, simple Monte Carlo simulations. Even though the estimates that go into these simulations might come from subjective estimates of experts, they appear to measurably improve the forecasts and estimates of experts. I show a couple of studies from the oil and gas industry, a set of studies that were done at NASA, but there's a lot of other studies where even relatively naive statistical models seem to outperform human intuition. And they are able to show that some subjective modeling methods measurably outperform other subjective methods, as long as they're dealing with actual quantities. So not qualitative, but quantitative methods. And We ultimately treat everything as quantitative. That's why my first book was called How to Measure Anything, because we're making the argument that you can measure anything. You've probably seen, if you're familiar with my work at all, that I spend a lot of time talking about calibration training for experts. This is an area where we find out that most people are subjectively overconfident. That means when they say they're 90% confident in some forecast they're making, they have a lot less than a 90% chance of being correct. And this is consistent with a lot of other research done by many other researchers. You can measure how calibrated somebody is simply by collecting their forecast and their probabilities that they put on those forecasts. Our early research showed that you could actually improve people's calibrated estimates for their real-world jobs, even if they were trained with trivia questions. In the last 22 years, we've trained over 1,600 people in these methods. And of those, we've collected 434 of the more recent participants and all of their test questions. And we've compiled that into a database of over 52,000 individual test responses on trivia questions. And as I said, training with those trivia questions actually does appear to improve your forecasting in your real-world jobs. A little over 20,000 of those 52,000 individual test responses were of the true-false variety. In other words, they were true-false questions about history, science, pop culture, etc. And you would answer each one true or false, and then you would state how confident you were in your answer being correct. If you were absolutely certain, you would say 100%. If you had no idea, you'd treat it like a coin flip, 50%. Otherwise, you might say 80, 90, etc. We would plot that on a chart like this. And I'm going to show you the results of a lot of that data plotted on a chart like this. Are they actually right 90% of the time when they say they're 90% confident? Now, I show a couple of dashed lines here that are pretty close together. Given our sample sizes, this represents the statistically allowable error for how far off of the ideal calibration line you could be. You don't have to be exactly right 70% of the time of all the times you say you're 70% confident, but you want to be within some statistically allowable error. This is the 90% confidence interval around ideal calibration. So anywhere in there is pretty close to good enough, okay? Here's how we actually did in the training that we provided. The red curve here shows how people did on their first calibration test, pretty overconfident. That's consistent with a lot of other research. Whenever somebody said they were 90% confident on their first test, these are a list of true-false trivia questions, they were right only about 75% of the time on average. And of all the times they said they were 100% confident, they're right less than 90% of the time. Now, after training, they did improve. They didn't quite get within the ideal confidence band there, but they improved by a lot more than chance alone would explain. Of all the times they said they were 90% confident, now they're closer to 85, 86% chance of being correct, but they could do a little bit better. Now, there's some other research that actually shows that people can be trained to be better at forecasting things subjectively, and that training applies to their real-world forecasting performance on real-world things like the chance of a major data breach if you're in a cybersecurity area. Philip Tetlock had tracked over 150,000 forecasts from 743 experts in world affairs. Now, Philip Tetlock was the researcher who did the 20-year-long Good Judgment Project. So he's done a lot of research in this space. This isn't even part of that. This is a separate study he's done. And he looked for things that made some people better forecasters than others. One thing he found out is training made a difference. So if you had some preparation in the form of basic probabilistic thinking and calibration training for that matter, you tended to forecast better. He also found that aptitude made a difference. He measured aptitude by test and by past performance. The test included things like job-specific aptitude test, and he also included IQ test. I'm not suggesting that you give your staff IQ test, but since IQ is supposed to be more or less stable over long periods of time, past performance is probably a good indicator. If they performed well in the past, maybe that indicates they've got an aptitude for this sort of thing and may perform well in the future. There was also a third thing he identified that was a good indicator of good forecasting performance, but we're going to circle back to that. We're going to talk about these first couple of things. Here we are again with our chart where we showed the effects of calibration training, how well they did before the calibration training, how they did after calibration training, and how they got a little bit further to go before they are within the statistically allowable error band. Here's another thing that we can do to further improve it. Tetlock mentioned that aptitude does make a difference. Well, we looked at the performance of individuals, of the 434 individuals that were in this database that we've compiled. And some people were answering the trivia questions in a way that they weren't much better than randomly guessing. They tend to be better than getting 50% right, but a lot of them weren't much better than that. So we took out the bottom quartile of people based on their trivia test performance. Now, their percent correct on the true false is not a measure of how well calibrated they are. That's a separate issue. These people in the training, they didn't get better at trivia from the first test to the subsequent test. This is a difference in how well calibrated they could be. Did they pick the right probability of being right? It didn't change their chance of being right. They were just better at picking the probability that represented that, okay? So some people could get 80% of the trivia questions correct on the true-false test, and some would only get 58%. 58% was about the cutoff, where they weren't doing much better than random chance. So if we took out that bottom quartile in terms of performance to kind of reflect what Tetlock found in terms of aptitude, making people better forecasters, well, that moved it up a little bit, actually. We find that after you took out the poorer performers there, you got a lot of points now within the statistically allowable error. There's still too many errors on the 100%. You have to be right every time you say you're 100% confident. And you'll notice that before the training and after the training, people are actually underconfident on the 50%, on the other end of the scale here. In other words, they're right more often than 50% of the time. And when they say they're 50% confident, and they're right by much more than chance alone would allow. So apparently they pick something that they prefer. They prefer true or false, one over the other, but perhaps they're choosing 50% because it feels more conservative, but they're overusing it. So there's one more thing that we could do. We can divide up the test questions into two groups. We can use a training set of questions and a test set of questions. From the training set of questions, we're going to compute a set of adjustments that could be applied to other questions. So the training set is used to compute adjustments for a completely different set of questions. And when we do that, we find that we can get just about entirely within the statistically allowable error band. This is, instead of taking their raw estimates and plotting them here, what we're doing is we're taking their adjusted estimates. And we're saying, once we adjust their estimates based on the training data, how well calibrated are the actual outcomes? And this is what we observe now. There's another issue, though, when we use subject matter experts for estimating things subjectively. They're pretty inconsistent in addition to being overconfident. And calibration training does not adjust for inconsistency. You have to apply some different methods to adjust for inconsistency. If you give subject matter experts a big, long list of things to estimate, and they estimate each one of them, in fact, you make the list so long that they won't know if you repeat some items in the list. They'll forget by the time they answer it a second time. If they're perfectly consistent, they should give the exact same answer the second time as they gave the first time. But instead, what we usually observe is that there's inconsistency. As long as they don't remember what they said the first time, they'll put down a slightly different answer, sometimes a very different answer the second time. This has been measured in several different industries and professions. And it looks like a large source of error in a lot of subject matter expert estimates is just personal inconsistency. If you could remove that error, you can actually improve their forecast. And we've applied this in many different fields ourselves. In cybersecurity, for example, we've got a lot of data just in cybersecurity. About 21% of all the variation in expert responses is due to personal inconsistency. They just would have given a slightly different answer next time. Now, these results are not just unique to probabilities. They could be applied to project cost or patient recovery times or how much money new movies are going to make, et cetera. It can be applied in many different areas. If you could just statistically smooth out the inconsistency of an expert, you end up with better forecast. Well, The lens method that I describe in some of my other work is one way to do that, but there's a simpler way too. You could just ask multiple subject matter experts and average them together. Averaging multiple people together would tend to reduce a little bit the inconsistency of the individual experts. So this brings me to the third item that Tetlock mentioned. He found that in addition to training and aptitude, one of the things that made people better forecasters was teams, but not just any teams, some teams with some caveats on them. So we're going to look at the performance of teams of people that are trying to estimate things. There's a lot of research on this. It's gone back to the 1960s, research that looked at how people were selected for teams and how they were trained once they were in teams, how their responses are elicited from the teams. Do you just get them all in a room and they argue until they come up with a consensus? Or do you ask them to come up with their own estimates separately and average them together? All right. By the way, the first one, getting everyone in a room and coming up with a consensus, might actually be one of the worst methods. That doesn't work very well. Asking people to come up with their own estimates and averaging them does slightly better, but there's a lot of other performance weighting and other mathematical methods for aggregating multiple experts. If you have a selected team that you've selected well for to optimize a particular set of forecasts, and you've trained them, and you're using the optimal elicitation methods, and you're aggregating them, their individual responses mathematically in a way that's meant to improve forecast, what you've done is you've created a new SME. We'll call that the Franken-SME. The Franken-SME is really just the aggregation of multiple other SMEs put together in a way that actually measurably outperforms any of the individual SMEs. So let's take a look again at our last set of calibration data. Here's the red line again, where people started out at the beginning of training. And now the yellow line represents not just people who were trained and people who were filtered to take out the people who weren't doing much better than randomly guessing, but we also used training data to come up with adjustments to the test data. And those adjustments put that test data in almost perfectly aligned calibration. So here's the question. What if I asked the question, how well would two people do if they were estimating these same sets of questions? What if I could pair them together and see how well the pair does? In fact, what if the pair doesn't even communicate with each other? They don't even know each other. All I'm going to do is use the data I already have. I'm going to randomly generate pairs and then ask, given that pair's responses, of all the pairs that had those responses, what percentage of them are correct? Well, in the case of the true-false questions, I'm going to deal with a special case here. I'm going to look at pairs that agreed, and not just whether it was true or false. They agreed on it either being true or false, but they also agreed exactly on their level of confidence. Like they both said it was true and they're 80% confident, or they both said it was false and they're 90% confident. If they both agree on the level of confidence on the same response to the same question, what's their chance of being correct combined? Again, these are pairs of people who don't know each other. All you know is two different subject matter experts who are doing better than just randomly guessing are being combined in a way to improve their forecast. What do we observe of all the people, of all the pairs of people who said they were 80% confident, and of all the people who said they were 90% confident in a pair? Here's the surprise. A pair of people who each said they were 80% confident have more than an 80% chance of being correct. Sometimes that's even true even if they haven't gone through calibration just yet. But it's certainly better if they've gone through calibration training, and even better still if they've been adjusted with a training set of data so that their responses are then further adjusted based on their past performance. So in this case, somebody who says, if you've got a pair of people who said the answer to that question is true and we're 90% confident, they're actually right more than 95% of the time. If those two people said they were just 80% confident, they're right more like 87% of the time, and so on. This is a huge improvement. This might be counterintuitive, but this isn't a math error. In fact, there's a theoretical basis for why this should be. Let me explain this. It all comes from Bayes' theorem. And if you've seen me talk about these things before, you're familiar with my talks about these things, or maybe you're familiar with it from other sources. Bayes' theorem is fundamental to a whole branch of statistics, how you deal with updating uncertainties. Okay, this is critical to that whole field. It's fundamental to probability theory itself. And if I can combine this with a few other basic axioms in probability theory, I can actually answer questions like, what's the chance of putting two experts together if they have these individual levels of confidence? What's the chance that those two experts will turn out to be right when they're combined? Well, it comes down to this equation right here. You can actually derive this equation from some of the other things I just mentioned. This is a way of computing what's the chance that two people will be right when they both agreed, even if they didn't know each other. Now, this makes sense if you think about it like random sampling. Suppose I'm randomly sampling how many grams of food there are in various packages that come off a production line. Now, you're doing your own random sample and I'm doing mine. And after some limited set of random samples, I conclude that there's a 90% chance that there's more than 100 grams of food on average in each package. And you do the same thing. Your sample, you're able to demonstrate there's more than a 90% chance that there's more than 100 grams of food in each package. We don't just average our responses. When we combine our samples, even though they were taken independently, when we take our samples and put them together, we can be more than 90% confident in our claim. And this theory actually supports that. So let's test the theory with all this data that we've got. I took my data set of the 20,000 plus true false responses from the 434 individuals. I generated over 380,000 random pairs of individuals. And I would look at situations where one person said they were 80% confident that the answer was true. The other person said they were 70% confident that the answer was false. Now, in the second case, that second person's really saying there's a 30% chance the answer is true. So I normalize it so everyone's talking about the probability that it's true. So if you said you're 80% confident the answer is false, you're basically saying there's a 20% chance the answer is true. So now the responses, instead of ranging from 50% to 100%, they range from 0 up to 100%. And I want to ask the question, if I have a set of responses of a particular type, like let's say there's a bunch of responses where one person said that it was 40% likely to be true and the other said it was 20% likely to be true. There's a bunch of responses just in that group. And then there's a bunch of other responses where one person said 90% and the other person said 100%. And we can look at how often each of those are correct. Well, if I can apply this math, I can try to predict what the actual performance in the data is. And here's what we observe, just based on that equation, which is a simplified equation, by the way, because it leaves out things like how well correlated the individuals are. If they're perfectly correlated, you can imagine that, well, that means they always both give the exact same answer. The second person doesn't even add information. They actually have to agree. They have to disagree sometimes. And by virtue of disagreeing, when they do agree, that means that you're more confident in their response in those fewer times when they do agree. So they have to be uncorrelated to a certain degree. All right. So here's how the model did at predicting the outcomes. I don't know if you can tell if you're familiar with statistical methods, but an R square of 0.9885 is about as good as you ever see in something like this, in any kind of research. That's a really high R square. Each dot represents some particular combination of responses. Like one dot would be all the times when one person said they were 80% confident that the answer is true, and the other person said 60% confident the answer is true, right? And another dot is a person said it was 10% likely to be true, and another person said 40% likely to be true. So those are each of those pairs, and there's a bunch of responses in each of those individual dots. Now, you'll notice that a couple of the dots are a little bit further off the line. Some of those are because there are combinations of responses that are rarer than other responses. Like there aren't too many cases where one person in the pair said they were 95% confident, and the other person in the pair said they were 5% confident. So that specific combination shows up less often than some of the other combinations. So that might explain some of the random error here, but still very strong model, especially since we're leaving out some stuff like how well correlated the individuals are in their responses. Here, they're not going to be very correlated at all, simply because they don't even know each other. But if they both do well, you can imagine that if you had two people who were Jeopardy grand champions, and they get 99% or nearly 100% of the questions right on the true false test, well, then of course they're going to be highly correlated too, because they're both going to do well in their responses. So we don't observe too many people like that. So there are some mathematically minimum requirements for how correlated people end up being, but they also tend to be a little bit more correlated than that because they tend to find the same answers to be easy or hard, right? So maybe lots of people would find the question, does a kilogram weighs more than a pound, true or false? Maybe a larger part of the population finds that an easy question to answer, for example. So that brings us back to Tetlock's research on teams. He did focus on aggregating teams' responses mathematically. There's been a lot of other mathematical publications on aggregating teams. It's all Bayesian and so forth. I'm showing you, again, a relatively simple solution without the covariance matrices or anything like that. So I don't look at correlations at all. But Tetlock went further and he said, beyond the mathematical aggregation, how can I further improve the performance of teams? Because it turns out that not all teams work equally well together, even if the individuals might be calibrated or good forecasters. One of his requirements for a good team is they had to be made of belief updaters. A belief updater is someone who's just willing to change their mind when they're given new information. It makes sense that if someone's willing to change their mind given new information, they're probably going to forecast better. But this doesn't appear to be a universal trait among people. There are a lot of people who, when they collaborate with their peers, they don't change their minds. In fact, they double down and they become more confident in their original forecast, even though they're disagreeing with everybody else. The disagreement itself causes them to be more confident in their original forecast. They double down. Well, Tetlock finds that that type of personality does not fit well with a team that's meant to forecast. He needs what he called belief updaters. So he tracked their responses over time, and he would track whether or not they changed their response. Teams that consist of belief updaters are generally going to perform better. Other research in educational psychology, for example, finds that the capacity to update your beliefs based on new information, the capacity to change your mind, might actually be an indicator of intelligence too. And that was another thing that Tetlock looked at in terms of aptitude, that simply the ability to change your mind might actually be evidence that you're just generally more intelligent. And that also seems to be correlated with forecasting better. So just to summarize what I've talked about so far, first, calibrating SMEs is absolutely critical. Your SMEs are providing estimates that you're using for big decisions. This is a critical measurement instrument. And a measurement instrument that's doing something this important needs to be calibrated. You need to understand its performance. And the performance of individuals is not the same as the performance of the team. The team is more than the sum of its parts. There's different math for that. People behave differently. It really is a separate entity by itself. It's not the same as just the collection of individuals. And we find that the research shows, and our data shows, that some aggregation methods are much better than others based on how the SMEs are selected for the teams in the first place, how they're trained, how those estimates are elicited from the teams. Are they all put in the room together, like I mentioned before, and then they come to consensus? That's not a good response. Or are there other methods for aggregating them, maybe making separate estimates and then aggregating them mathematically somehow? And finally, how the SME estimates are combined mathematically. There's multiple methods for that, and some, again, are much better than others. This is so critical in so many areas of business operations. It's not just cybersecurity, but it could be, major mergers and acquisitions, big IT investments, big R&D investments. Think of all the ways your organization relies on the estimates of subject matter experts. And you have to ask, what is the performance of that method? Now, some of the research that I mentioned earlier that looks at how to aggregate multiple experts, one of those researchers was Roger Cook, and he came up with methods for computing performance weights for subject matter experts based on their past performance. We applied this method in a particular case. We trained a bunch of terrorism experts in Washington, D.C., and we applied Cook's method for coming up with performance weights for these estimates. And Cook found something similar to what Tatlock found in separate research and to what we have found. When you compute the performance weights of all the experts on a team, you end up having to ignore most of them. More than half of the experts end up with a performance weight of 0. Now, that might cause a little bit of anxiety because that means that perhaps half the people here might not be good enough at forecasting that they would even be included in a forecasting team like this. But that's what Roger Cook's research found, and we find similar things. So there are small groups of people who are better forecasters. They're better by enough that you can't explain their performance improvement by chance alone. They can be trained to be even better, and they can be mathematically aggregated in even better, superior ways. So that brings me to the end of my session here. This is important stuff. This is central to so many big, important decisions in any organization, whether it's, as I said, cybersecurity risk or enterprise risk or other big investments of any kind. Figure out how well your teams estimate things. What is the performance? How well calibrated are your teams of SMEs? How good is your Franken-SME? For questions, you can email me at dwhubbard@hubbardresearch.com. Thanks.